Okay, section 2 from chapter 7 deals with second order differential equations. Okay, so second order differential equations, they contain d2y dx squared. So they could contain first order differentials as well, but they must contain at its highest the second order. So let's have a look at actually finding the solution to this. Right, so we're going to integrate it twice to find what was differentiated twice to give us 12x. So let's integrate it once. So if I integrate the second derivative with respect to x, that will give me the first derivative. Yeah? And then I integrate this to obtain the first, the y, so undo the differentiation. So this is what will happen to the left hand side. So let's integrate once. I'll have dy dx, that's equal to the integral of 12x. So dy dx gives us x squared over 2, so it's 12x squared over 2 plus c. So that's 6x squared plus c. Now we just need to integrate again. To obtain y, and that's the integral of 6x squared plus c. So that's going to be add 1 to the power, divide by that power, so 6x cubed over 3 plus cx, and then plus another c, well, let's use k. So y is equal to 2x cubed plus cx plus k. So the second order differential equation created two constant terms. Okay, so that is the result. Now let's have a look at example 6. So in this example, we are going to look at the general solution to more complicated equations. Now, I'm going to go through the method. I'll do a separate video where I explain why this method works. And to begin with, this section considers only equations of second order when they are equal to 0. These are called homogeneous differential equations. So of order 2, so second order. So I will go through steps very carefully, and then we can generalize it in the next section. So first of all, you need to do the following. You need to rearrange it so you always have the second derivative followed by the first derivative followed by y at the end, and you've got to have equals 0 on the other side. The second thing, we are going to write auxiliary equation, and we are going to replace the second derivative with m squared, the first derivative with m, and then constant 3y becomes a constant term, and this auxiliary equation must be a quadratic. Okay, and then we need to solve the auxiliary equation. So we're going to factorize it. And we're looking for the solution. So this one has a solution m is equal to minus 3 over 2, or m is equal to minus 1. Now, depending on what kind of solution you obtain, whether you obtain two distinct solutions, like here, real solutions, or repeated solutions, or imaginary solutions, you will have to go and write the solution in 3 different ways. So if there are 2 real solutions, then the solution to this equation is going to take the following form, and it's going to be y equals, and it has a times e to the power, and you take the first root, 3 over 2x, and then plus b, e to the power of the second root. And that is the general solution to this second order differential equation. Now this is general solution. Okay, where a and b are arbitrary constant. Again, notice we have two such constants in this equation. You had two constants in the other equation as well. Okay, now, so in those equations, let's just actually do the general form of these. Okay, so in general situation, when you're solving homogeneous equations of second order differential equations, you can have a d2y dx squared plus b dy dx plus c y equals 0. Then this general solution, you are going to obtain by solving the auxiliary equation. And the auxiliary equation is am squared plus bm plus c equals 0. Now, if you have two real roots, alpha, beta, then the general solution is y equals a e to the power of alpha x plus b e to the power of beta x, and you're done. When alpha and beta are the roots and a and b are just a constant that you might need to find when you look for a particular solution. If you have repeated root, so that's when your discriminant is equal to 0, let's say alpha, and the solution takes the following form: a, and then you've got in brackets a plus bx, when a and b are just some constants, e to the power of alpha x. And then finally, imaginary, I would say complex roots, let's say alpha plus I beta plus or minus. Okay, so the form is following. You've got y equals, you're going to have a e to the power of alpha x in front, and then a cos beta x plus b sine bx. Let me write it again. So you've got this e to the power of alpha x, so that's that real part that forms e to the power of alpha x, and then imaginary part forms the multiplier of the angle, so cos beta x plus b sine beta x. So that these three different situations are the only ones that can happen when you've got homogeneous equations of order 2, and you just need to memorize what happens when. So let's have a look at the next example. So the next example, example 7. So here we have to show that y equals a plus bx e to the power 3x satisfies the following differential equation. So when it asks us to show it, they're not asking us to solve this. What we're going to do, we're going to differentiate it once and substitute it into the equation, and differentiate it twice to obtain the second derivative, and obviously substitute both into the equation and show that everything nicely cancels out to become 0. So let's differentiate it once. So dy dx. So use the product rule, that's u and that's v. So we're going to differentiate u to obtain b. So it's b times e to the power of 3x. Plus we're going to differentiate e to the power of 3x to obtain 3e to the power of 3x multiplied by a plus bx. Maybe tidy it up by factorizing e to the power of 3x. So you're going to get b plus 3 times a plus 3bx. Let's differentiate this again. So d2y dx squared. So the way I wrote it, that will be my u this time, that's v. So it's going to be 3e to the power of 3x times b plus 3a plus 3bx. Add, let's see, leave u as it is and differentiate the bracket. So b and 3a go to 0, so we're left with 3b. I'll maybe factorize e to the power of 3x out, and I'm going to get 3b from this bracket and 3b from that, so 6b plus 9a plus 9bx. All I need to do now is substitute into our equation. Let's call that equation I. So on the left hand side I've got e to the power of 3x, 6b plus 9a plus 9bx plus, no, minus 6 lots of the first derivative, c to the power of 3x, b plus 3a plus 3bx plus 9, the y is over here, I'll just put e to the power of 3x first, and then a plus bx. So this is the left hand side of the equation. So let's factorize e to the power of 3x. We are left with 6b plus 9a plus 9bx minus 6b minus 18a minus 18bx plus finally 9a plus 9bx. Okay, so how many b's have we got? We've got 6b and minus 6b, so they cancel. I've got 9a minus 18a and plus 9a, they nicely cancel. And finally I've got 9b plus 9bx minus 18bx, they cancel also. So you're left with 0, which is the right hand side, which is shown as required. Okay, example 8, we are asked to find the solution to this differential equation. You notice it's nicely already lined up, the second derivative followed by the first, and the y function equals 0. So the auxiliary equation that I'm going to focusing on looks like so. So this is a perfect square. So m is equal to minus 4. So this is the root, this is repeated root. So I know that what form it takes, y equals a plus bx e to the power alpha x. So in our case it's y is equal to a plus bx, these remain as constants, e to the power of minus 4x. Done. Really quick. Let's have a look at example 9. So here again we've got the second order differential equation. M squared minus 6m plus 34 is the auxiliary equation. Try to factorize it. Can't factorize it. Let's just test the discriminant. So it's 36 minus 4 times 1 times 34. That's going to be less than 0, so imaginary, well, complex roots. So let's find those roots. Whichever way you want to find them, I will use the completing the square form. That's going to be okay. So it's m minus 3 all squared is equal to minus 25. So that gives me plus or minus 5i. So m is equal to 3 plus or minus 5i. So the general solution is going to be e to the power of, remember, alpha x, and then you've got a cos beta x plus b sine beta x. So e to the power of, this is the real part, so 3x, a cos 5x plus b sine 5x. There you go. So now you're ready to go on to exercise 7b. I can show you all the questions in that exercise.